Should we start? We're all here. Okay. So I started writing just because I wanted to get this. I wanted to get this out of the way. Last time, Nikolai is here. So last time, I shown you the following theorem. So we have this asymmetric variant of the disjointness problem. Okay. So in this variant, Alice and Bob get some strings, some Boolean strings, and each string has two. So n times 2k many bits. Okay, so each player gets a string, and these strings have n blocks of 2k bits each. Now, Alice, this is an asymmetric setting in the sense that in each string, in each block of 2k bits, Alice has exactly 2k bits set to 1. So the size of her set is n times k. But Bob, in each block of 2k bits, he only has 1 bit set to 1. So the size of his set is n. Okay? And it's asymmetric, and we have shown, using the richness technique, last class, we have shown that there is no, okay, so let me say it that way. In any AB protocol for disjointness, either Alice sends at least n times k to the 1 minus 2 delta bits, or Bob sends at least n log k bits.
One more time, how many bits has Bob?
So they both have, both players have a string which is n times 2k bits long.
Yes.
Okay. So, but Bob, so we have n blocks. This string is n blocks. You split to n blocks, and each block in the string of Bob's has only 1 bit set to 1.
Okay.
Right. So you can think of each block as being a number from 1 to 2k. Right? Okay. And now I'm going to...
What is delta?
Oh, sorry. Delta is actually... so either Bob sends at least delta n log k. So there's some constant c such that this holds. So we've proven it last time, it was 1/5. Okay. Okay, so, and now we have this data structure problem, which is called partial match. And in this problem, we would like to encode a subset of d-bit strings. And we have capital N strings in the subset. That's a parameter of the problem. And the kind of queries that we'd like to be able to answer is, well, I have some pattern P, which you can think of more or less like a regular expression. It's not really, it's just a partial assignment. So I have a partial assignment P to the d bits, and I want to know, does there exist any element of the set which matches this pattern? Meaning, where the pattern is 0, x needs to have 0. Where the pattern is 1, x needs to have 1. And if the pattern is star, x can have either 0 or 1. Right? So I want to encode this set of d-bit strings in such a way that I can answer these queries quickly. Okay? And today we're going to show, let me remind myself. So in any SWT scheme for partial matching, so we're going to show a lower bound on the query time. So the number of probes must be at least either, let me see, d by w or d by log s. Okay, so any data structure schema, the number of probes that it makes, morally, so let's say w is not very big. Let's say w is 1 for example's sake, then you must query at least d bits. It's not a very strong lower bound, and I believe that this is open, so open. You know, the best upper bound that we have is actually d times n. D times capital N, so, you know, can you improve this? Improve this.
You haven't completed the sentence. Either t is greater than or.
No, no, that's it. Oh, either. Sorry, it must be. So it's either t must be bigger than this, or it must be bigger than this. So that's why I wrote either. We have. All right. Okay. So and all right. Okay. So now let's prove. So this is proven. So this theorem is proven by reduction to disjointness. So suppose we have an SWT scheme where T is little o of both of these things. Okay, then we're going to build a protocol for disjointness. We're going to build a protocol for disjointness where both A and B are little o of n log k, which cannot be by our lower bound. Okay, so here's what we're going to do. Alice is given, so now we want to solve disjointness. We want to reduce disjointness to this problem. So Alice is given her string, and let's call these bits A11 up to A12k, etc., up to N2k. Okay, so these.
Is it good that N, capital N, doesn't appear in your lower bound?
No, it's not good, right? It's not actually. That's right. It doesn't appear. I know it's, and actually, so the best upper bound that we know requires N. I need to read basically I think the best algorithm we know basically needs to read the entire S. The best algorithm that I know actually is the trivial one. And you're right. It sucks that we cannot even make capital N appear there. There's actually a reason for it, and the reason is that the size of the query itself is d bits. And basically the only lower bound techniques that we have are kind of information theoretical. So, you know, if Bob can send the entire d bits, there needs to be no dependency on n. In the communication, you know, the communication cost of this problem is d bits. And since this is actually the only known technique to prove lower bounds for static data structures, there's really no hope of doing better using these techniques. So we need something like radically new, and right, in order to prove that. Okay, so all right, so now we show that if we have this scheme where I do less than this, then okay, so then I have a protocol for it. Okay, so now I introduce disjointness to this. So let's call Alice's string is this thing. So we have 2kn bits, which I'm aij, and let me call Bob's string b1 up to bn, where I think of each of these as an element of this set 2k. Okay, so these are the inputs for Alice and Bob, and now we need to do a reduction. For this, we're going to use the following. So let f is going to be some smart encoding. So f is going to be a map from 2k into strings of length 2l with, say, l bits, with l bits each. So the only requirement that I have is that L is large enough so that all the strings of Hamming weight L, all the strings of length 2L of Hamming weight L this set should be larger than 2k. So L, it's enough that L is something in the order of log k. Okay, some number times log k. And now notice the following interesting property if I have this encoding. Oh, let me also denote by f star to be f, but instead in the positions, in these L positions, instead of having ones, I have stars. Okay, and now here's an interesting property. F star of I matches f of j exactly if I equals j. Meaning, so in this string,
F star consists of zeros and stars only.
f star consists of zeros and stars,
Okay,
and it's some encoding of the number I. And now if I have any different encoding where you have ones and stars, because the Hamming weight is L in both cases, there has to be a 0 where this guy has a 1. Right? Okay. And this is the key property. So now I want to encode, now I'm going to encode Alice's input as a set S, and I'm going to encode Bob's input as a pattern P. Okay? So here's what I do. So I go over Alice's input, and for each Aij, which is equal to 1, and only for those that are equal to 1, I put the string, the following string into S. So it's a string, it's going to have n blocks, 1 up to n. In each block I have 2L bits. Okay? And on all the blocks except the ith, I put zeros. And on the ith block, I put f of j. Okay? So for each of these bits, aij, I look at the bit, and if it's 1, then I'm going to add, let's call this string xij. I'm going to add it to my set S. So S is the set of xij's such that aij is 1. So that's what Alice does. And then Bob constructs, so I say I, but this is Alice, right? Alice. And then Bob constructs the pattern P, where in each block you put f star of b, b1, and in the ith block you put f star of bi, and in the nth block you put f star of bn. Okay. So now look at the following nice property. P matches xij. When does P match xij? So these patterns f star of whatever always match the zeros, because f star only has zeros and stars, right? So the only issue is at coordinate I. And in coordinate I, by this property, f star of bi matches f of j if and only if. So this matches if and only f star of bi matches f of j. And this happens, as we've seen, if and only if bi equals j. Right? So, but now I don't include all xij's in S. I only include those such that aij equals 1. Right? So so that means that P matches some string in S if and only if there exists a j such that aij. So there exists some ij such that aij equals 1 and bi equals j. Meaning Bob has a j. Bob has on the ith block. Bob has the jth bit turned to 1. And Alice also has the ith bit, the jth bit in the ith block turned to 1. So that says if and only if A intersect B is non-empty. Right? And that's the reduction. So now the players simulate the data structure. Bob does the queries, sends the queries to Alice, and Alice sends back the answers. And, you know, because the time is little o of d by log s, in total the communication that is done is d. Right? So how much is d? I kind of forgot to do that. So how much is d? So d is n times 2l, right? Which is order of n log k. Right? That's what d is. Right? So now if t is very small, then the number of total bits that Bob sends to Alice is going to be little o of n log k by log s times log s, because that's how much he pays per round. So it's going to be little o of n log k. And if t is also smaller than d by w, then the total number of bits that Alice sends is again little o of n log k. So you get this. Okay, and that's the reduction. I had a blank last class, so I could have easily done it then. But can I? Is that? Shall I? Are you? Shall I? Yeah. Okay. Right. So today, today I would like to show. So the ultimate goal today is to prove the following theorem, or mostly prove the following theorem. The predecessor problem, and maybe I should redefine what this is. So predecessor problem, where we have a set of size n, and what did I call the other parameter? So it's n. I have n, and it's m and n, right? It's m and n. So let's just call it m n. Okay. So what's this? Maybe I should have done it in the other order, but. So in this problem, I want to encode a set S, which is a set of m-bit numbers, m-bit natural numbers, and I have n of them. Okay, and then the queries. So a query is an m-bit number, and I want to find the largest element of S which is still smaller than Q. Right? So we have our set S. It has n elements, and now I ask some query, and I basically want to know where it goes, the position that it goes. That's the predecessor problem. And today we'll show that schemes for this predecessor problem need let's say that we want to encode this in polynomial in n many words, where each word has size order m, which is reasonable. Then I need to have t to be at least square root of log n by log n. And this turns out optimal.
So why it's optimal?
Right, so it's optimal because of a very clever algorithm by Beam and Fick.
You mentioned it last time.
I mentioned it last time. So it's optimal. No, it's not at all obvious. No. So, a binary tree can do log n. After there was some really clever algorithm called fusion trees that could do square root of log n, using the fact that, that basically we can get m bits every time. For every probe you get m bits. And so somehow this can be used to speed it up. And then everyone thought it was square root of log n, but then Beam and Fick proved simultaneously that actually you could get this, and they proved the lower bound. Okay, and this lower bound is very difficult. I actually read it at some point, unfortunately, because a few years later it turns out Sandeep Sen proved a much simpler version. And when I read this in the literature, I kind of didn't pay so much attention, well, because I read the other proof, why would I bother? And while I was proving this, while I was trying to, and then I forgot this, and then when I was trying to prove this thing, I went back to the previous best-known proof, and it was very complicated, so I tried to simplify it, and it turns out that it was exactly what Sandeep Sen did. So today, but the proof might be slightly different because the way I've simplified it uses stuff that I'm comfortable with. And I don't know because I haven't seen his proof in the end, but it's probably underlying. It's probably the same ideas. But so it turns out that using a bit of information complexity, you can, or the tricks that appear in that literature, you can prove this not so hard, and that's what I'm going to try and do. Okay, but for that, let's give some definitions. Okay, kind of the crucial definition is a T, A, B, A, or T, A, B, B protocol. So what is this? So this is a protocol that works in rounds, and you have T rounds. In each round, only one of the players speaks. That's either Alice or Bob. Whenever Alice speaks, she sends A bits. So it's A bits per round. Not A bits in total, but A bits per round. So it's a little different notation. When Bob speaks, he sends B bits. And this says that Alice starts, and this says that Bob starts. So here Alice has the first round, and here Bob has the first round. So that's what a TAB, A or B protocol is. And okay, and now let me give you some other definition. So it's kind of a direct sum. So this theorem is proven by a sort of direct sum argument. And for that, what do I mean by direct sum? So suppose we are given a function f, which is some function from x cross y into z. Okay. Then I'm going to define the problem f. Let me see which one I have here before. It's fr1. fr1. So fr1. So this is a communication problem, right? Alice gets x, Bob gets y, and then they must find out f of xy. And now I'm going to define another communication problem. So it's a communication problem where Alice gets r instance of x. Okay. Bob gets, well, we'll see what they get, and maybe we'll fill it later. So this is a communication problem. We all understand that. So what's f of r? So this is not t. So this is 1. What's f of r1? In this problem, Alice gets r instances of x. She gets x1 up to xr. Okay. And now Bob, he gets a few things. He gets an index I in R. He gets the very same first R minus 1 instances, x1 up to I minus 1. So he gets the first I minus 1 instances. And he gets some string y. So all of these guys come from x. And this y comes from y, as you'd guess. And what they wish to know is they wish to output f of xi y. Okay, is the problem clear?
It seems that all the previous x's are irrelevant.
Indeed, so exactly, so what happens is exactly that. So Bob knows so they actually only want to compute f on one of the x's. And Bob knows which of these x's, he knows the index of this x, right? But Alice does not know that. Alice knows the various x's.
I see.
Right, so Alice knows the various x's, but she doesn't know which one matters. Okay? Now suppose that you have a multi-round protocol and Alice is the first to speak. So then Bob, but Alice is the first one. Yeah.
Bob also knows part of some of x's, right?
Right. So Bob also knows basically all the x's up to and excluding the one that he cares about. Right.
If all x's are different,
Not necessarily. They could be the same. But Bob, Bob doesn't know. In fact, there will be some distribution on this, and Bob, but here's what we like to understand. So only Bob knows the index. Now suppose only Bob knows the index. Among all these x's, only Bob knows which one really matters. So now suppose Alice is has to send the first round. Intuitively, you kind of see that she doesn't know which x matters, so the best she can do is kind of send a little bit of information about each of the x's. Because if, say, she sends all the information about x1, well, it could be that I is x2, then this is completely lost. And we're actually going to show this in a very formal sense, that this is actually the case. So what will happen is that when you have a protocol like this, and Alice is the first to communicate, if the number of instances is much bigger than the number of bits she sends, you can basically get rid of the first message, because it doesn't matter. You incur a bit more of error. It's going to be probabilistic protocols. You incur a bit more of error, but it doesn't matter. Okay. So more precisely, we're going to prove this theorem. So it sends round elimination. It says the following. Let me copy. Suppose f of R1 can be solved as by a T A B A protocol. And this is a probabilistic protocol. Okay, so I kind of didn't say that, but it's a probabilistic protocol, and it's success probability or error probability with error probability epsilon. So in this protocol, Alice and Bob share some randomness, and then they communicate, and then for every input, the probability that they're wrong over the shared randomness is most epsilon. Okay. Then there is again probabilistic T-1 A-B-B protocol for F with error, and then it's going to be epsilon plus square root, or 2 times square root of A by R.
A by what?
R. So R is this number here. Right? Which kind of is, and okay, so now I'm going to give you I'm going to tell you how this proof is done. Here's how it's done, very shortly and intuitively. So to do it formally, it takes a bit of work, but here's how it's done. So Alice is the first to communicate, and then we're going to show that the typical amount of information that she can send about this ith coordinate, as I varies, think of I as being like a random coordinate, then the typical amount of information that she sends A bits, But the typical amount of Shannon information that she sends about the ith coordinate, the one that matters, is only going to be A by R on average. Okay, and we'll show that. Then it so happens that if instead of using this message, I just choose one where I pick kind of the message at random, that's going to do just as well. Because this message has so little information that basically if I just pick it from the same distribution but not conditioned on X, then that's going to work fine. Okay, and this is what we're going to prove. And so you lose kind of this much in terms of success, in terms of error. Okay, and to prove that, I'm going to use a few facts. Okay. Right. So let's see. So definitions. Maybe we all know or not. And if don't, so this proof relies on this kind of heavily. So if I have, say I have some random variable which is distributed over some finite set. We all know what entropy is. Good. We all know what conditional entropy is, then I assume. And hopefully we all know what mutual information is. Possibly conditioned. Yes? Okay, good. All right, so then maybe we also all know these very nice properties that these things have, and I'm going to write them down. Okay, so symmetry, lemma or proposition. The information is symmetric of X and Y. I guess I'm not even going to use this, but this is a cute property. So, and I wrote it here, I don't know why, but so I'm just going to write it again. And, let's see, the information between X and Y is at most log of the size of the support of X. We all know that. Here's something which maybe if you're not used to. So suppose that Z is obtained by some function of X and W. Sorry, and W. Then it just so happens that, and this function might also have some extra independent from everything else random bits. Then, so it's a random function. Then the information between X and Z given Y and W, Y doesn't really matter for this. So this is going to be the information between X and Z given W. Okay, so I can remove Y. If F does not depend on Y, I can basically remove it. And I get it's exactly the same amount. Okay, so I need that. And the chain rule. Chain rule. So if I have several random variables, the mutual information between conditioned. So I don't have space, but this could be conditioned on Y, is at most the sum of the information of Xi given, of Xi and Z given X1 to Xi minus 1. Right. Okay. And Pinsker inequality. Pinsker's inequality says that if okay, so let X and Y be random variables. Okay, And for this, and for each, and let y given little x be the, the random variable y conditioned on, or let's call it just yx, is the random variable y conditioned on the event x equals x. So these two could be correlated. So x and y could be correlated. Yx is the distribution, let's say, of y conditioned on x being x. Then it just so happens that if I do the average, so if I pick little x according to the distribution of x, and I look at the average L1 distance between y and yx, then this is at most 2 times square root of the mutual information between y and x, or x and y. Okay, so this is what I'm going to need. So this, and here, okay, so and this tells you, that for all intents and purposes, it doesn't matter. It doesn't, for most x, you expect that if I use the distribution y, which is obtained over all x, instead of the distribution y, which depends on x, specifically, I'm not going to see much difference because the L1 distance between these two, on average over x at least, is actually very small. Provided that the information between y and x is very tiny, I might as well use y instead of yx. And that's how you can use. That's always how Pinsker is used in these arguments. Okay. Oh, also Yau's principle. Yau's principle. Which says that the randomized communication, so maybe I'll just state it, because I'm guessing we all know. So the randomized communication complexity of a certain protocol equals the error probability of the worst randomized protocol equals the error probability of the best deterministic protocol under the hardest distribution, under the distribution that maximizes this, right? So we could write the communication complexity of solving some certain task or function, whatever. What do I know? So this is probably not how I want to write it. Let's say the error. So I want the error for solving this task f by protocols of a certain length or something. This equals the maximum over all input distributions for this function of the minimum over all protocol pi of the error that pi makes on mu. So I'm just going to. So we all know this. Okay. Right. Okay. So now let's try and prove Sen's round elimination. So here's what I want. I want to construct a protocol for f, a randomized protocol for f, using randomized protocols for f of R1. Right? And I'm going to use Yau's lemma. So here's what I'm going to do. So let mu be a distribution over the inputs of f. Okay? Mu is a distribution. I'm going to construct a deterministic protocol so I'm going to assume that protocols for FR1 exist, and I'm going to construct a deterministic protocol for f that uses one less round than the protocol that does this. Okay. Right. So yes, I feel like this.
I'm sure that in the conclusion of the theorem you have f and not FR1. R1.
This?
Yes.
Yes, that's actually, yes, that's right.
Okay.
So f of R1 has much larger input, right? So than f.
Yes.
Right? So in principle, but on the other hand, this protocol has one less round.
I see.
Right. Okay. So what do I need in order to get a protocol, a protocol for f with some error probability, here's what I'm going to do. I'm going to let the adversary give me any input distribution mu for f, and I'm going to build a protocol with this much error for that input distribution. Okay, so let mu be any distribution, right? Any distribution of inputs for f. Okay, so now what I'm going to do, I'm going to take mu and I'm going to construct an input distribution for f of R1. And then I'm going to use, so I'm always using Yau's principle here, so and then I'm going to use that by Yau's principle for this input distribution for f of R1, there will have to be a deterministic protocol with their epsilon. Okay, so how do I build this distribution? So maybe, you know, let's, you know, this is kind of the universe, so let me be clear. So, okay. So how do I build this distribution? So now we construct mu tilde, which is going to be an input for, you know, domain of FR1. So how do I build mu tilde? So here's how it goes. So again, Alice, let this be a random variable which is distributed according to mu. X and y is the random variable, so it could be correlated, right? Alice and Bob. So Alice and Bob get x and y distributed according to mu. And now I'm going to build an input for f of R1. Here's what I'm going to do. I'm going to I'm going to use shared randomness, and I'm going to pick, so maybe this isn't, let me think of it. Well, okay, so before I do that, let me just build mu tilde. Okay, so here's how I build mu tilde. Okay, so first step, I pick I in R uniformly at random. Okay, that gives me my set I. So let capital I be this random variable. Okay, and then I pick xi and y according to mu, according to the distribution mu. And then I pick x on all other coordinates according to the marginal mu x. So it's independent. So I pick for all other coordinates other than the one that I care about, I pick x from the same distribution, but independently of y, exactly.
And of x2, I guess. Of that x, y.
I
mean, you have picked already x sub I.
Right. So now I'm picking x1.
Then you will everything.
Yes, exactly. So x r, and xi does not appear there, right? So not I. And all of these I pick independently according to the same marginal distribution that mu gives to x. Okay. So from Alice's point of view, her x's look exactly the same, right? R. From Alice's point of view, her x's look all exactly the same, and she's the one to send the first message. So this is my mu prime, by the way. So so then what happens is that I give these guys xi minus 1, I, y. I give these guys to each player, as in the protocol. Okay, so now, this is my distribution mu prime, and now by assumption there has to be some deterministic protocol for which solves f of R1 on this distribution with error no larger than epsilon. Right? And so let pi 0, and the first message is sent by Alice. That's our assumption. And so let pi 0 be this message. So it's a random variable. It is the first message of pi. And what does that depend on? Well, it only depends on x. Right? So that's pi 0. It's some random variable, it has this distribution. And then there's the rest. Okay. Right, good. So, okay, so what do I know about this pi 0? I know, first of all, so it will reveal some information about these various x's, right? So how that value is going to be the Shannon information between the various x's, x1 up to xr, and pi 0. And let me look at this information from the point of view, well, I guess it doesn't matter. So, okay, so it will reveal some information. And I could look at this information from the point of view of Bob. But I guess I don't care. And the reason I don't care is because of this property. So the Shannon information between x and pi 0, so pi 0 is a function of x, right? So it doesn't, so whether I condition or y or not, I get the same value. That's the first. Maybe I actually don't need that, but we'll see. In any case, these two are the same, so I can put it there if I want. Another thing to observe is that this is at most a, right? So the Shannon information, why? Because the number of bits of pi 0 is a. Pi 0 is the first message, only a bits, so the Shannon information between x and pi 0 is at most a.
Protocol is deterministic,
Yes.
but then emitter information is 0.
No, because the protocol is deterministic, but the inputs are given by some distribution. Right. So here I'm using Yau's principle. Okay. So what am I doing? I'm trying to build a probabilistic protocol for f. By Yau's principle, this is the same as the following: you give me any input distribution, and I build a deterministic protocol for f, which attains the same error on that specific distribution. Okay, so that's what I want to do. You give me mu, so let mu be the one that you give me, and now I want to build a deterministic protocol for f, which attains error epsilon plus 2 square root of r on this mu. Okay, and for that I'm going to. What am I doing? I'm constructing an input distribution for this problem f of r1. Now again, by Yau's principle, supposing that f has randomized protocols with error epsilon, then for this input distribution mu prime, there has to exist some protocol which is a deterministic protocol and which succeeds with error at most epsilon on this distribution mu prime. Right? Okay. And so this pi 0 is, as you said, a deterministic function. It's just a function of x. But x itself is not. X has some input distribution on it. In particular, the distribution of this x bar is each xi is going to be picked according to the marginal of mu. And on the specific on the magic coordinate, this actually is furthermore correlated with y. Right? So what I'm saying is that this information is not 0. Well, because on one hand, x bar is picked according to mu. It has some entropy. It's whatever entropy mu x has times p times r. And pi 0 also has some entropy, because it uses the entropy of x. Pi 0 is not a function. Pi 0 is the mass. So pi 0 is a random variable which is obtained by applying the pi 0 function to the random variable x. So are you following?
I'm still confused. If x, so pi 0 follows from x. If x has some value, then the value of pi 0 is fixed.
Yeah, pi 0 is a function of x, but x is a random variable, so pi 0 is also a random variable.
Yeah, but.
So I'll give you an example. Suppose that pi.
Distribution of pi 0 given x is concentrated on one element.
Yes.
Yes.
And that means that common information actually equals the entropy of pi 0.
Yes.
Yeah.
Yes.
Ah, okay.
That's
Yeah.
what you.
Oh, so
I
yeah,
see.
yeah,
I see.
was
Yeah.
mistaken.
Yeah. Okay. Right. And whatever. And because of that, it's at most a. Right. Okay. Okay. So now by the chain rule, this thing equals the sum for, let's call it. I'm going to try. So j equals 1 to r of the information between xj and pi 0 given x up to j. So I'm going to use this notation. This denotes x1 up to xj minus 1. Right? So that equals. Now here's a subtle and delicate point which appears on all these kinds of proofs, which is I'm just going to make some claim, and we'll see why it's true. J equals 1 up to r of the information between x and pi 0 given x up to j. I can furthermore assume arbitrarily that I happens to be j. Okay, and now, right, so now this is delicate. So what is this? This is the information between these two random variables conditions on x. It's some average over some difference of entropies of certain distributions. Yeah. Capital I is this random variable.
Okay.
Is this random
Just
variable?
have not the best notation because you have two capital I's. One stands for information and one stands for.
Oh, I see. Oh, that's terrible. You're right.
So that's why
You're
I
right.
made it.
All right, so let's call it j. So that's a good, that's actually, so let's call it j. Why not? Let's call it j.
Now you will say that j is equal to 3, okay.
Right, so j, yeah, capital J equals little j. So, but why is this true? Because pi 0 is a function of the x's, right? And the x's are completely independent of j. So j and the x's are picked independently. So all these random variables have the same distribution, whether j equals j or whether j equals 1 or whether j equals anything. So I can assume that j equals j and I get exactly the same value. Okay? But now notice the following, which is, now this quantity is actually equal to it's actually, sorry?
Confused. So. So it means that we can assume that bit trend in the j is every time is a little j that runs.
Yes, exactly. Yes, that's what it means. That means that when Alice sends the first message, j could be anything. So it might as well be, well, this one, whatever, the one that I'm measuring the information about. It's the same because all of what's happening here is independent of j. But now, okay, so now is the kind of the magical step, which appears in all papers that use these kind of things. So this I can multiply and divide by r, right? 1 over r. Right? But this happens to be r. So this value here is the mutual information of x and pi 0 condition on x up to j, up to capital J. So, sorry, x, I meant j there, right? So I'm missing j. So it's going to be x capital J and pi 0 and j. By definition, this is the probability that j equals to.
Little j is replaced by capital J.
Yes. Yes. Okay. And all right, and then what we conclude? We conclude that this information, so the information between the important coordinate, the information between the coordinates that I want to compute f of, and the first message is at most a by r. And presumably r is much larger than a, so this information is actually very tiny. And this is what I meant by making precise the intuition that the first message will tell you nothing about the important xj because Alice doesn't know what it is and she has to decide what message to send. Okay, so let me just write that. So the information between xj, which is the coordinate we want to know the function about, and pi 0, given x on average over all the previous x's and this j, this is at most a by r. Okay, so this is concluded. And then we can conclude by Pinsker inequality that, if I take the expected, so now what does this say? So I pick a little j according to the same distribution as capital J. I pick some instantiation for all the guys up to j according to this distribution. And then I expect that the distance, and now let me write pi 0. Okay, so I'll just write it in kind of very big. We have space. So the distance between the distribution of the first message. Oh, and I also pick, then I also pick xj. And the distance between the the distribution of the first message conditioned on j and on x up to j, and the first message, when I actually also know xj, this is small, is at most 2 square root of a by r. Yeah.
Let us return to previous step. So I'm a little bit confused with the transition to the second from below row.
This one?
From this one to the following one. Yeah.
Okay. Well,
How? So the previous row was obtained in the assumption that the distribution doesn't depend on j capital, so we can assume that small j, the j capital, equals to j small for
Right.
each.
right, this shows that this guy equals that guy.
Yeah, but then how we come from the average to from this sum to information of xj about known p0.
So this is by definition. So the information between, so the information between, let me just write that. So the information between A and B given C is the average over C when little c is picked according to big C of the information between the same distributions conditioned on big C being little c.
Okay, so
That's the definition.
that's just one of the properties that wasn't listed. Oh,
Yeah,
okay,
yeah,
yeah,
okay.
okay. So then it's clear. Thank you.
And now you can conclude that, what does this say intuitively? It says that, for the typical little j and x up to little j, the two distributions of pi 0 when you know x little j, and pi 0 when you just take the average over all little j's according to the right distribution, these are actually close. So what it says is that knowing little j makes hardly any difference on the distribution of the first message. Overall, over the next, if you take the average over the remaining guys. Right. Right.
You need to
Okay.
change the I in the original thing, on the left, the bottom left. No. Is that now J also?
Yeah. Yeah. All right. So now what do I do? So now how do I get a protocol for F? Okay. So Alice and Bob now Alice gets some x and Bob gets some y, and they're distributed according to mu. Okay. So now what they're going to use shared randomness, and they're going to pick from the same distributions as here. They're going to pick a j and x up to j from the same distributions. So you pick a number j from 1 to r at random, and then you pick j guys from the and then you pick j minus 1 x's from the marginal of mu. Okay. And then Alice, what she does is she sets xi to be equal to x, and she picks, using her own private randomness, she picks x I plus 1 up to x So I guess she can also use shared randomness. Does it matter? No, I guess it might matter. Let me think. No, I guess it doesn't matter. It doesn't matter. So they also pick, so they basically pick all coordinates except the jth one. And then what do they do? Is that true? Yeah. No, actually no. Actually, it's not true. So Alice is the one that needs to pick this because only she knows. Okay, so besides j and x up to j, they also pick pi 0, conditioned on these. No, is that fair? Yes, no, exactly. So they pick pi 0 conditioned on these. So what's distribution of this pi 0 is the distribution that pi 0 would have if you had seen this, and you would assume that x is actually distributed according to its distribution, and the remaining guys would be distributed according to this distribution, right? And right, that's x0. And then what Alice does is she looks at these guys, x up to j, pi 0, and her own input x, and she uses private randomness to pick from the distribution x of the remaining guys. One from the conditional distribution on knowing that these guys would have, on knowing this guy, on knowing this guy, on knowing this guy, and so on. And then what they do is, and then they run the rest of the protocol as if the first message was pi 0. Okay, so that's what they do. And this is the protocol pi prime.
Yeah, but the only thing to observe is that we constructed the randomized protocol.
Right, and yeah, right. I haven't finished yet. Okay, that's true. I still need to get my hands on a deterministic protocol. I've built a randomized protocol. And now,
can we use Gauss principle? Can we say that randomized complexity is equal to worst case, so maximum over distributions over randomized protocol?
you can. It's actually the same.
That's what we can just do instead.
We can, because if we have a randomized protocol, right, because if we have a randomized protocol for that works with some success probability over some distribution, we can fix the random choices of this protocol so that it also works with the success probability over the same distribution. Well, we still need to kind of claim the, I guess we're done, but from this, right?
Yeah, of course. Yeah. We have to consider probability, of course.
Yes. Okay, and that's it.
Yeah, I'm saying that instead of talking about deterministic protocols, all time we are talking about randomized protocols.
Yes, and we could do that, and then we're done. Yes. And that's it, and that's the proof. So now you have to show that the error probability of this protocol is basically, this at most the error probability that the old protocol had plus the distance plus the average distance, and you can show that. And I'm not going to do it because it's.
Oh, yeah, well,
Shall I do it? I guess I can.
Yeah, it's intuitive, it's clear.
It
If
seems-
you write formulas, it won't become more clear.
Right. It's you have to sum expectations. So I sketched it just before class, and it seemed to be okay. So you have to do sums with the expectations, and then you extract them, and you see. I can tell you, like, the only trick to solve the sum, so the success probability is going to be, some sum over the probability that your pi 0 tilde message, which is that, so let's, your pi 0 tilde message equals some message times some probability of success conditioned on this message, right? And the trick to solve this is now, well, you can add here, you can subtract and add here the probability that the real pi 0 equals this message plus this probability that the real pi 0 equals this message, right? These two, you put them outside, and by triangle inequality, this one is at most 1, so by triangle inequality, they're going to be at most this. And the other thing is the... Right, and we're not done, and we have 13 minutes. Is that right? Okay. We're all, I mean, we still haven't proven the theorem, but we've proven at least the round elimination limit. 15 minutes. Is that what we have? 15 minutes. Okay. And it's still a bit, okay. Right, so I thought this class was too tight, but okay. All right, so this is how you prove it. Direct sum argument. And now, okay, so now what do we want? And now we do, and now we have to use it. So okay, so now let's try and prove this. And okay, so yeah, all right. So and I'm going to hide like the exact square, but we'll see. So all right, so okay, so let's try and prove the theorem. So suppose that we have a so we have this predecessor mn schemes, right? That means that we have a t, so that's the number of rounds, and then Alice sends w on each round, and Bob sends log s on each round. Right? So this log s, I'm just going to call it L just to abbreviate. And who speaks first? Bob speaks first, right? So if I have such a scheme, I have this protocol for the same problem. So I have a protocol for what's problem. So you know, for the function f, where f, Alice gets a set, Bob gets a query, and they have to output, you know, the min x in s, the min x in s, such that x is at most q. Right? So if I have a scheme for the predecessor, then I have a TWB protocol for this function. Okay. Okay, so now I'm going to show you that if I have such a protocol for this function, then I also have a same thing, TW log s, maybe I'll just write it every time, B protocol for, so this is predecessor with parameters m and n, and then, let me just copy from my notes. I don't have a lot of time. Then I have a for predecessor where the number of bits has gone down by r, and right, number of bits has gone down by r. The size of the set is the same, and it's 1r. Okay, so Bob gets our copies. Okay, let's show. So this I'm going to show. Okay, so why is this the case? So in this problem, let me see that. So in this problem, Alice, what happens? So Bob has the R instances, and Bob has a query Q. So right, so Bob has Q1 up to Q R, and each of these queries is a number with m by r bits. Right? I'm looking at this problem, pred, which is this 1r thing. Okay, and in this problem, Bob gets Q1 up to QR, and they have, you know, m by r bits. And what does Alice get? Alice gets Q1. Alice gets some index j, right? She gets Q1 up to Qj minus 1, and she gets a set S of m by r bit numbers, and the size of S is n. Correct? Okay, so this is the problem. And now they want to solve, now they want to know the predecessor of Qj. Now they want to know the predecessor of Qj in S. Right? Okay. So here's what they're going to do. They're going, and okay, so now we do that by reduction to this pred mn. Okay, so here's what we're going to do. Bob just takes Q, the instance to this problem, he takes it to be the binary concatenation of these numbers. So it's the number which is obtained by concatenating the binary representation of these numbers. How many bits does Q have? Well, m bits exactly. Okay, so it is a valid input, very valid query to this problem. Okay.
Please don't have the same prefix, then the number, and then zeros.
Yes, exactly. Exactly. And now Alice constructs the set S prime, which is the set of, you just do Q1, Qj minus 1, and then you do Xi, and then all zeros for all Xi and S. And then they run, so now they have an input for this problem, and then they run this protocol. And what happens is that the predecessor of Qi, notice that, so in the binary representation is exactly the same up to here, and then on the ith position you have Qj, so on the jth position, this appears on the jth position. Right? And then on the jth position, what you're doing is you're comparing Qj with Xi, with each Xi, with x1, x2, x3, right? So what I'm saying is that the predecessor of Q in S prime has the predecessor of Qj in S as its jth block. So if they learn the predecessor of Q in S prime, then they also learn the predecessor of Qj in S. Okay, so this is the reduction, right? All right, so I start with this. Now I have this. And now I do round elimination. So by round elimination, I must have a t minus 1 w log s a protocol for this guy. Okay. And I've eliminated a round by Bob, and now I need to tell you how to eliminate a round by Alice. So now I'm going to do another reduction. I'm going to take this guy, and I'm going to build a t minus 1 w log s a protocol for, and now let me be careful, predecessor of so there will be some R2 here, some other parameter R, and the number of bits used to be m by r, and now I'm going to lose log R2 bits, and the number of elements used to be n, and now it's going to be n by R2. Okay. All right, let me try, and it's for R2. So now here Alice gets R2 and Bob gets 1. So it's kind of this, so it's symmetric. Okay. So what is this problem? Okay. So in this problem, Alice gets R2 sets, S1 up to SR2. Right? And what does Bob get? He gets some coordinate j. He gets S1 up to Sj minus 1, and then furthermore he gets some. Let me just say. So these are sets where each Si has n by 2 elements, n by R2 elements, and all the elements have these many bits. Okay. And Bob gets j, the sets up to j, and then he also gets some query q, and this query q is just the string with these many bits. So what do they do? And now they need to come up with an instance for this, an input for this problem that allows them to get the answer. Here's what they do. They do S. S is going to be the union of the string 0001 concatenated with everything from S1 with the string. So I take the string I take. Let me make it. So here's what S is. I go over every number in S1 and I prepended the number 1 in binary. And then I go over every number in S2 and I prepended the number 2 in binary, and so on. Until I reach SR, so SR2, sorry. And I prepend it the number R2 in binary. Okay, and this is my S, is the union of all these guys. Okay, and now notice that I want to query. So I basically want to query Sj. So what I'm going to do is I'm going to use J union Q. J, the binary representation of J concatenated with the binary representation of Q. That's my number. And now I just communicate. And what happens is that this J forces this number to be somewhere, the predecessor is somewhere on JSJ. And then if I know that predecessor, then I know. So this is the reduction. Okay. So now I do this, and now by round elimination, I have a T minus 2 W log S B protocol, where protocol for predecessor of this thing, m by r minus log r2 n by r2. Okay. And now I'm basically back where I started. Of course, the inputs are a bit smaller. Right. And now, so now I'm not going to do this because it's a terrible calculation, but
for which R2 do you do that?
For which?
So you need to choose R2.
Right, yes, exactly. You need to choose R2. And how do you choose R2? So you try to choose R2 to be as small as you can so that the error is still, in the end, the error should be less than 1/10. Okay? So you do this, you're going to do this, these two things, you do them T by 2 times, right? And the error in the end is going to be...
R2 be large enough, because R2 is in the denominator of your overhead, right?
Right. R2 is in the denominator. Oh, you're right. You mean here?
In your sense around elimination.
Right. You want R2 to be big.
Yeah. On the other hand, it can't be big because you divide by it.
Exactly. So you need to be careful. Hello. You need to be careful, and all right. But in the end, so how much error do you get in the end? You're going to get T times square root of A by, let me make sure I don't make a mistake.
R2.
A by R2, is it R2? Because A by R, sorry, A by R plus square root of B by R2. I think that's it. Right, and what's A and B again? So A is actually W, right, W, and B is log S, right? Right, and so actually, okay.
So T is equal to this or so?
T?
Yeah, that is Kaizen right now.
So what's T? So and then,
So what are you saying?
so this is the error. So the final error. The final error in the end.
Plus an original epsilon.
Right. But I guess when we started, the protocol was perfect. Let's just do deterministic data structures. But of course, you could have assumed that there was some error there, right? So this is the error. And now, so now I'll just tell. Now it's a terrible calculation, and I don't want to do it, but it's in the notes, and I've done it. But I'll tell you the kind of what you'd get, what you need to choose in order to make sure that it works. You need to choose, so now you're aiming for, so now you're aiming for a contradiction. So if you choose T to be at most half times log n by log n, then this forces you to choose n, which is the set numbers, to be something like 2 to the 1/2 of log m squared by log m. And then you choose R1 to be something like t squared times w, and R2 to be something like, R1 to be t squared times log s, and R2 to be t squared times w. Does that make sense? No, that's probably the other way around then. Sorry.
No, it's okay because R and R2 goes into denominator, and then you will.
Right, but it's the other way around, actually.
Yes, it's the other way around. Yeah,
Right. R2 and R1. Right, and for these things, if you just work out now you do a lot of calculations, and you conclude that once you reach the end, you have a zero. So once you reach the end, you still have that. So what do you need? You need something like m by r to the t by 2, r1 to the t by 2 should be super constant, and the same thing should happen for n to the r2 to the t by 2. However, the error is less than 1/10 or something. And this is a contradiction because you have like a non-trivial problem which you're solving without communication. Okay, so and that's kind of not, I could do it, but it works out. Okay, and that's how you put that. Okay. Any question? Good. Yeah, we're done. That's nice. Thank you. Thank you.